lapel.
Learning her principles of biochemistry. Chapter 2, Water, the solvent of life. Ionization of water, weak acids, and weak bases. Pure water is slightly ionized. Have you ever wondered why water is often referred to as the universal solvent? Well, it all comes down to the fascinating properties of water molecules. Water molecules are made up of 2 hydrogen atoms and 1 oxygen atom. Due to the difference in electronegativity between hydrogen and oxygen, water is a highly polar molecule, which means it has a slight positive charge on the hydrogen side and a slight negative charge on the oxygen side. These polar water molecules are attracted to each other and form hydrogen bonds, creating a network of interconnected molecules. This hydrogen bonding is what gives water many of its unique properties. The ionization of water is expressed by an equilibrium constant. Have you ever wondered why water is such a unique and important molecule in biological systems? Let's start by understanding what happens when water ionizes. Water, as we know it, H2O, can undergo a process where it forms equal numbers of hydrogen ions, hydronium ions, and hydroxide ions. This process is crucial for many biological reactions and is expressed by an equilibrium constant. Now, equilibrium constants might sound a bit intimidating, but they're actually quite simple. They're just a way of expressing the extent of ionization of water at equilibrium. The equilibrium constant for the reversible ionization of water is denoted by the symbol Kw. At this point, you might be wondering, what does all of this have to do with pH? Well, the pH of an aqueous solution reflects, on a logarithmic scale, the concentration of hydrogen ions. The equation for pH is pH equals log H+, where H+ represents the concentration of hydrogen ions. But how does all of this relate to biological systems? The answer lies in the concept of buffering against pH changes. Buffers are like the unsung heroes of the biological world. They're mixtures of weak acids and their conjugate bases that help maintain a stable pH in living organisms. In summary, the ionization of water and the concept of equilibrium constants play a crucial role in maintaining the delicate balance of pH in biological systems. Understanding these concepts can help us appreciate the intricate chemistry that underpins life as we know it. The pH scale designates the H+ and OH- concentrations. Hey there, welcome back to our chemistry series. Today, we're going to dive into the fascinating world of the pH scale and how it designates the concentrations of hydrogen ions, H+, and hydroxide ions, OH, in a solution. So, what exactly is the pH scale? Well, it's a way of measuring how acidic or basic a solution is. The scale ranges from 0 to 14, with 7 being neutral. Anything below 7 is considered acidic, and anything above 7 is basic. Now, let's talk about the ion product of water. This is the basis for the pH scale and is expressed by the equation. Essentially, it tells us the concentration of hydrogen ions, H+, and hydroxide ions, OH, in any aqueous solution. The pH scale is logarithmic, not arithmetic, which means that a change of 1 unit on the pH scale represents a tenfold change in the concentration of hydrogen ions. For example, a solution with a pH of 3 has 10 times the hydrogen ion concentration of a solution with a pH of 4. To put things into perspective, a cola drink with a pH of 3.0 has in concentration approximately 10,000 times that of blood, which has a pH of 7.4. That's quite a difference. In the lab, the pH of a solution is measured using a pH meter, which gives an electrical response proportional to the concentration of hydrogen ions. This is one of the most important and frequently used procedures in biochemistry and medical diagnoses. The pH of a solution affects the structure and activity of biological macromolecules, so a small change in pH can cause a large change in the function of a protein. Box 2-to-1 on being one's own rabbit. Don't try this at home. Have you ever heard the phrase being one's own rabbit? It sounds intriguing, right? But what does it actually mean? Let's break it down. The term being one's own rabbit refers to the idea of using oneself as a test subject for scientific experiments. It's a concept that dates back to the early 20th century. In the world of science, researchers have often used animals, particularly rabbits, to test the effects of certain substances or procedures. However, in some cases, scientists have taken on the role of their own test subjects to study the effects of various experiments on the human body. The phrase being one's own rabbit was famously used by J.E.B.S. Haldane in his book Possible Worlds in 1928. Haldane and his colleague, H.W. Davies, decided to experiment on themselves to study how the body controls blood pH. They conducted experiments involving alkaline and acidic substances, such as sodium bicarbonate and hydrochloric acid, to understand their effects on the body. Their bold approach led to groundbreaking insights into the regulation of blood pH and the body's response to different chemical stimuli. Now, it's important to note that being one's own rabbit is not something to be taken lightly. It involves significant risks and should only be undertaken under the strictest ethical and safety guidelines in a controlled scientific setting. In modern science, the phrase serves as a reminder of the dedication and sacrifice of researchers who have fearlessly pursued knowledge, often at great personal risk. So, the next time you hear the phrase being one's own rabbit, remember the incredible stories of scientific pioneers who pushed the boundaries of knowledge in the name of discovery. Weak acids and bases have characteristic acid dissociation constants. Let's break down the term acid dissociation constant. It's a mouthful, but it's actually quite simple. The acid dissociation constant, denoted as Ka, tells us how readily an acid donates a proton in a solution. The stronger the acid, the smaller its Ka value. And guess what? We can use titration to determine the amount of an acid in a given solution. In a titration, we gradually add a strong base, like sodium hydroxide, to a solution of a weak acid. As we do this, we measure the pH to create a titration curve. This curve helps us understand the acid's behavior and its characteristic acid dissociation constant. Now, let's talk about the Henderson-Hasselbalch equation. This equation is like a magic formula that relates the pH, the concentration of the weak acid, and the concentration of its conjugate base in a buffer solution. It's super handy for understanding buffer action and acid-base balance in biological systems. Speaking of biological systems, buffers play a crucial role in maintaining the pH of our cells and tissues. They resist changes in pH when small amounts of acid or base are added. It's like having a built-in defense system against pH fluctuations. And there you have it. Weak acids and bases might sound intimidating, but they're essential players in the chemistry of life. With their characteristic acid dissociation constants and buffering abilities, they keep our biological systems in balance. Titration curves reveal the pKa of weak acids. First, let's understand what titration is. Titration is a technique used to determine the concentration of an acid in a solution. It involves adding a solution of a strong base, usually sodium hydroxide, to a measured volume of the acid until it is neutralized. As the sodium hydroxide is added in small increments, the pH of the solution is measured. This data is then used to create a titration curve, which is a plot of pH against the amount of sodium hydroxide added. Now, here's where it gets interesting. The titration curve reveals the pKa of the weak acid. The pKa is a measure of the strength of the acid and is related to its tendency to lose a proton. The lower the pKa, the stronger the acid. This means that a lower pKa indicates a greater tendency for the acid to lose its proton. Each weak acid has its own unique titration curve, and the midpoint of the curve corresponds to the pKa of the acid. At this midpoint, the concentration of the proton donor equals that of the proton acceptor, and the pH of the solution is numerically equal to the pKa. So, titration curves provide valuable insights into the behavior of weak acids and help us determine their pKa. Understanding the pKa of weak acids is crucial in various fields, including biochemistry and medicine. Thanks for joining us in this video. Stay tuned for more videos on the world of chemistry.
PharmaPal.